Hey everyone, welcome back. We have covered eigenvalues and eigenvectors for 2 by 2 matrices, and now it is time to tackle 3 by 3 matrices. This involves a bit more calculation, but the principles are the same. Let's dive in. Remember, eigenvalues are the values lambda that satisfy the equation A times V is equal to lambda times V, and eigenvectors are the corresponding vectors V. We find eigenvalues by solving the characteristic equation, which is given by determinant of A minus lambda I is equal to 0. Let's take the given 3 by 3 matrix A. We will be finding its eigenvalues and eigenvectors. We begin with the characteristic equation, which is given by determinant of A minus lambda I equal to 0. And this gives us determinant of 1 minus lambda minus 1 0, negative 1 2 minus lambda, negative 1 0, negative 1 and 1 minus lambda is equal to 0. On solving the determinant, we get 1 minus lambda. We'll be taking this as the minor. So that's 2 minus lambda times 1 minus lambda, and we have negative 1 minus of minus 1 times negative 1 into 1 minus lambda minus 0 is equal to 0. Further, simplifying this section, we get 2 minus 3 lambda plus lambda square minus 1 over here. This is plus minus 1 minus lambda is equal to 0. It can be seen that 1 minus lambda is a common factor in both the terms. We factor out 1 minus lambda and we have this simplifies to lambda square minus 3 lambda plus 1, and we have this negative 1 here is equal to 0. This gives us 1 minus lambda, lambda square minus 3 lambda is equal to 0. Therefore we get 1 minus lambda, we can take lambda common and we will be left out with lambda minus 3 is equal to 0. Thus, we get the values as lambda is equal to 0, 1 and 3. These are the 3 eigenvalues of the given matrix A. Now next, we will be finding the eigenvectors corresponding to each of these eigenvalues. Let's start with lambda equal to 0. To find the eigenvectors, we need to consider the equation A minus lambda times I into V is equal to 0, where A is the given matrix, lambda is the eigenvalue, I is the identity matrix of order that of A, and V is the eigenvector which we wish to find. Substituting lambda equal to 0 here, we get A V is equal to 0, that is 1, negative 1, 0, negative 1, 2, negative 1, 0, negative 1, 1. V we will be putting up as x1, x2, x3 is equal to 0, 0, 0. Now we are going to use row operation to reduce this matrix to its corresponding row echelon form. So on R2 we perform R2 plus R1, and this gives us first row unaffected. The second row will become sum of this, this and this. So we have an entry 0 here, then 2 minus 1 is 1 and negative 1. Here we have 0, negative 1 and 1, followed by x1, x2, x3, and on the right we do not encounter any changes, so this is going to be 0, 0 and 0. Now we focus on the third row, trying to make it 0. So we perform on R3, R3 changes to R3 plus R2, and this gives us first row as it is, second row as it is, and the third row changes to 0, 0 and 0. And here we have x1, x2, x3 is equal to 0, 0, 0. Rewriting back in the equation form, we get x1 minus x2 is equal to 0 from the first row, and x2 minus x3 is equal to 0 from the third row. So thus we have from the first equation x2 is equal to x1, and also from the second equation we have x2 is equal to x3. So thus we have x1 is equal to x2 is equal to x3. So the eigenvector is going to be v1 is equal to x1, 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 where x1 is a real number. If we put x1 as 1, we get v1 is equal to 1, 1, 1. This is the eigenvector corresponding to the eigenvalue lambda equal to 0. Now let's move on to the next eigenvalue, which is lambda equal to 1. Substituting in the equation, we have a minus I times v is equal to 0. And this gives us 0, negative 1, 0, negative 1, 1, negative 1, 0, negative 1, 0 times v, which will be x1, x2 and x3 is equal to 0, 0, 0. Here we see that R2 has all non-zero entries, so we will be exchanging R2 with R1. So we perform the ERO, R2 exchanges with R1, and as a result we get the matrix this times x1, x2, x3 is equal to 0, 0, 0. Now we are going to reduce this entry to 0, and for that we need to perform R3 changes to R3 minus R2, which gives us negative 1, 1, negative 1, 0, negative 1, 0, 0, 0, 0, and here we have x1, x2, x3 is equal to 0, 0, 0. Rewriting back in the equation form, we get negative x1 plus x2 minus x3 is equal to 0, and from the second row we get minus x2 is equal to 0, which gives us x2 is 0. Putting this in equation number 1, we get minus x1 minus x3 is equal to 0, or x1 is equal to minus x3. Therefore, the eigenvector corresponding to lambda equal to 1 is given by x1 0 minus x1, where x1 is a real number. If we put x1 as 1, we get v2 is going to be 1, 0 and negative 1. This is the eigenvector corresponding to the eigenvalue lambda equal to 1. Now moving on to the last one, wherein lambda is equal to 3. Let's get started. The starting equation would be a minus 3 times of I times v is equal to 0, and thus we get the corresponding matrix to be negative 2, negative 1, 0, negative 1, negative 1, negative 1, 0, negative 1, negative 2 times of v, which is x1, x2, x3 is equal to 0, 0, 0. We got to reduce this entry to 0. So for that we perform the ERO, R2 changes to 2 times of R2 minus R1. And as a result we get the first row remains as it is. Now for the second row, we perform the ERO 2R2 minus R1. So we have 2 times of minus 1 minus of minus 2, which gives us negative 2 plus 2, which is 0. So we have the first entry in the second row to be 0. The next entry is going to be 2 times of negative 1 minus of minus 1 is equals to negative 2 plus 1, which is equal to negative 1. The second entry being negative 1, and the third entry is going to be 2 times of negative 1 minus of 0. So this is going to be negative 2. The third row as it is times x1, x2, x3 is equal to 0, 0, 0. After this, we got to reduce this entry to 0, and for this we perform the ERO, R3 changes to R3 minus R2, which gives us first row as it is, second row as it is. The third row will be 0 minus 0, negative 1 minus negative 1, which is 0, and negative 2 minus negative 2, which is again 0, times x1, x2, x3 is equal to 0, 0, 0. Rewriting in equation form, we get negative 2x1 minus x2 is equal to 0, and from the second row we get negative x2 minus 2 times of x3 is equal to 0, the first equation can be rewritten as 2x1 plus x2 is equal to 0, and the second equation can be written as x2 plus 2x3 is equal to 0. From the first equation we get x2 is equal to negative 2 times of x1, and from the second equation we get x3 is equal to negative x2 upon 2, and substituting the value of x2 from here we get negative of negative 2 times x1 upon 2, which gives us x1. Therefore, the eigenvector corresponding to lambda equal to 3 is given by v3 is equal to x1, comma, x2 is negative 2 times x1 and x3 is equal to x1, where x1 is a real number. If we put x1 as 1, we get v3 is equal to 1, negative 2, 1. So that is the eigenvector corresponding to the third eigenvalue lambda equal to 3. Hope you realize that finding eigenvalues and eigenvectors for 3 by 3 matrices follows the same principles as for 2 by 2 matrices, but the calculations are more intricate. While the calculations can be tedious, understanding how to find eigenvalues and eigenvectors for 3 by 3 matrices is essential for mastering linear algebra. Remember to practice with different examples to solidify your understanding. If you found this video helpful, please give it a thumbs up and subscribe for more linear algebra tutorials. Let me know in the comments if you have any questions or suggestions for future videos. Thanks for watching and happy learning.